We have two people in the lobby. Is anybody else coming in? Let's see. All right, so I think I'll get started. Ho, ho, ho. Merry Christmas Eve. This is going to be a very interesting episode or live show of STEM Online Academy. Okay. For those of you who already know me and the channel, we're all about advancing your mathematical intuition by strengthening it through interesting concepts, through visualization, and advanced problem-solving techniques. Hey, just another internet guy. How you doing? It's good to see you again. Glad that you're sticking with the content and enjoying the content. I appreciate it. Perfect. Yes, today's going to be a Christmassy type of live show. It won't be as hardcore as the other live shows. The other live shows were rigorous. Today is going to be almost a relaxing type of theme, Christmas theme. However, we'll still do mathematics, but at a lighter pace, mainly through drawings and pretty much mathematical modeling and understanding concepts that way, but pretty much at a light pace today. Okay, nothing complicated. All right, so that's what's on the menu today. Okay, so ho ho ho, Merry Christmas to all. Okay. By the way, Justin, here, guy, you celebrate Christmas or no? Just want to know the audience out there. Okay. Okay, you do. Okay, so yes, thank you. I appreciate it. Yes. Yeah, I celebrate Christmas as well. But yes, thanks. Today, as I mentioned, right, is just going to be a very light approach to doing math, right? There'll be some Christmas puns involved as well. And at the same time, we're going to be learning, as I said, new mathematical methods, right? Not tricks, but mathematical methods through a very geometric approach, if that makes sense, not algebraic tonight, okay? So we're taking a break from the algebraic methods, all right? And as I said, all this stuff is from my book, right? So if you're interested, you can always look at my book in the description below. Okay, it will be at the end of the live show, obviously. Okay, so let's get started. Okay, so let me get to the screen here. Okay, let's get to entire screen. All right, I'm going to go to the whiteboard. Okay, as I mentioned, today is going to be a Christmas Eve special on Fourier transforms. Okay, now I know we've talked about Fourier transforms before. However, though, if you've seen my last episode, not the live show, the last stream, I post streams on what days? Thursdays and Sundays. Okay, last stream I talked about Fourier transforms. Okay, definition, reiterating the definition, and some theories on Fourier transforms. But I did something interesting in that stream. I talked about comparing Fourier transforms to Laplace transforms, okay, which was very interesting. All right. So if you haven't seen that stream, please look at the stream from before. That was a very cool stream. For those of you who are mathematically minded, you will enjoy that. Okay. Just want to make sure everyone is here. Okay. All right. All right. So let's continue. So as I mentioned, again, happy Christmas Eve. I don't know what you guys do for Christmas exactly, whether you make turkeys or open presents or whatever. I used to do the whole present thing. Not that much anymore with the presents. I feel like as you get older, the present thing just starts to die out. You know what I mean? But still, the celebration is nice. The holiday is nice. It's the break from a lot of things. And I think we all need it. Okay. But yeah, I like the family aspect and the food, of course. And I'm sure you guys can agree, right? Food and family aspect. Okay. So number 2, we're going to talk about what Fourier transforms really are. Okay. And what I mean what they really are is as signals, right? As pretty much taking signals and frequencies and breaking them down into their own sinusoidal components, if that makes sense, okay? Number 3, frequencies as structure. Number 4, the heat equation, right? What I mean by the heat equation is, a certain type of partial differential equation, okay? Now, I'm not going to go into the equation myself, right? I'm going to give you sort of just a conceptualization of how it works, okay? For more info on that, you can consult me on the heat equation during my free time. You can, ask me questions. My contact is in the link under this live show. Okay, number 5, simulation. We're going to talk about simulations on heat diffusion. That's pretty much what we're going to be doing with number 4. Okay, so number 4, 5 will be are linked. 6 is the wave equation. Okay, wave equation and oscillations. 7, if we have time for physical interpretations, because this is quite a bit, and I really want to condense today because today is I feel like it's a holiday. I don't want to over bombard your brains with rigorous math. Okay. All right. If there's no questions, yes, I am. Yes. Yes. Yasum Tikanis. Yeah. How did you know the last name was there? I think it's in my bio. Anyways, last name Masterakos. Yeah. Oh, okay. Yeah. Yeah, I can tell by that. Yeah, that name there. Yeah, it was great. Merry Christmas to you too. Yes, Merry Christmas. Thank you. Yeah, yeah, yeah. Yeah, it's a big holiday in my family anyway. So yeah. Well, not as much I don't really go for the presents anymore because I'm like I got it over. Oh, really? Are you like Greek from like Turkey or anything like that by any chance? Just curious how that works. Name is Turkish. Curious. Yeah, that's interesting. And your family's from Turkey? Yeah. I'm fully Greek. Grandpa was born in Turkey. Somehow got a Turkish last name. Yeah, yeah, yeah. Yeah, I don't want to go into the history of it, but I'm sure your family told you about the whole situation in Greece and Turkey, right? Uh, yeah, yeah. So you know what I mean. I don't want to get into politics here with everybody because I don't know everyone's nationality here, but yeah, you know what I mean, right? So it's complicated. Yeah. Part of Turkey was a Greek colony at some point, right? So yeah, 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 yeah. But anyways, that's for another discussion. Are you interested in mathematics, physics, or engineering? Any of these things, by any chance? What brought you to the channel? I am glad you opened up and got to the channel. In university, by any chance, or college or something? Oh, perfect. Well, I'm glad you found the channel because if you like mathematics, oh, then this is perfect. Yeah, this is perfect. This here, right? Okay, so my channel is all about that. It's all about discussing advanced math and physics concepts, right? For university students, right? Or going to be university students, right? Pretty much prepping them, especially first years, to develop strong mathematical intuition. First, second, and third year, because I feel like in high school they don't prepare a lot of students for university, if you know what I mean. I really feel like they don't, not at all. It's not even close. From high school to university, it was not even close. Yeah. Right. But just about a little bit about me. My background is in mathematics and physics. I went to university for that. Finished with a double degree. Yeah, that was a nasty degree. Very complicated, very very complicated. But yes, that's great that you're in second year computer science. Okay. You'll find this very handy. There's a lot of applications from math to computer science. Okay, so you're gonna notice, not just in this live show, but a lot of my live shows gonna be very handy, very handy. Okay, all right. So let's get back to the whiteboard. Okay, and Merry Christmas again. All right, so let's look at. So I was just going through what's on the menu today. Now, I may have to partition some of this stuff. What I mean by that is, since it's a Christmas holiday, I'm not going to go as rigorous in the math today. Mainly, as I mentioned again, for people who are coming in, it will be a concept first type of process. Well, all my live shows are concept first. But what I mean is mainly going through the mathematical modeling for a lot of these equations, right? And other things as well, okay? Mathematical modeling is handy because it first makes math come alive, right? It makes it fun. And you don't just see equations on the board and you're getting lost all the time, right? So I feel like having a visual spatial conceptualization of the problems is really handy. And I'm sure you guys can agree, right? Oh, yes, thank you. Merry Christmas. Oh, we have another person, 2 other people here. Great. Yatra Sanker. Yes, thank you. Thank you, Yatra. Merry Christmas to you too. Clev Vaus 3809. Hello, yes. Hello to you too. All right. What brings you to into the channel? Interested in mathematics? Need it for a course? Learning by yourself? What is it? What makes you interested in knowing more on advanced math? I always like to connect with people, get to know what makes them interested in stuff, if you know what I mean. All right. All right, so let me know what's going on. In the meantime, we're going to get started on the concepts. Okay, we're going to go lightly today, as I mentioned. So we're going to look at Fourier transforms, what Fourier transforms really are. Okay, so let's get to it. Okay, so we're going to look at number 1. What are Fourier transforms? Okay, so definition. Okay, DEFN. I'm going to use yellow. DEFN. DEFN is definition for okay, so the DEFN. Definition for Fourier transforms. Okay, let's look at what a Fourier transform is. So Fourier transforms. I don't know if any of you have heard of a Fourier transform. Some of the other guys have. I'm just going to reiterate this. Transforms. Any of you learned or know what a Fourier transform is? Yes, this is another guy. I know I have to repeat this, but it's so important. Okay, I hope you understand why I'm doing it. Yeah, exactly. Fourier transforms is decompose like a complex signal into sinusoids. Okay, that's what they are. Exactly. Just another guy's got it, right? So we're just going to write this down. Fourier transforms. Exactly. Fourier transforms are the superposition, I'm going to say superposition, of sign. Let me see here. I'm going to use a different coloring here to emphasize what I'm talking about. Superposition. Okay, superposition. And I'm underlining for a reason here. Superposition of let's see how. Yeah, exactly. 1 second. Yes. Superposition of complex signals. Complex signals. Okay. But in reality, right, when you decompose them, these complex signals, they become sinusoidal waves, right? Right. The decomposition decomposition is just sinusoidal waves, just sinusoidal waves. Okay. All right. So that's what a Fourier transform is. Okay. That's the, well, I wrote a phrase, but in reality, the way we calculate the Fourier transform is the following: curly f for Fourier, okay, of f of t as a function of t is equal to the integral from minus infinity to infinity of f of t times e to the negative I omega t dt. Okay, and that's how we calculate the Fourier transform. So if you know integration, there's nothing. If you know improper integration, there's nothing complicated about this. Okay, any questions? Okay, any questions on this? Okay, so this is what a Fourier transform is. Okay. If there's any questions, I will proceed. Okay, so no questions yet. Okay, so what we're going to go to, right, is I may bring up an actual visual of what I'm talking about here. Okay, so let me just go to the desktop. Okay, and let me just give me a second here. We're going to stop sharing temporarily, and I need to go all the way over here. Okay, we're going to go to the desktop here. I'm going to show you exactly what I'm talking about. Okay, hopefully you guys can see what is happening. Okay, you see that I have a mathematical model up. All right, hopefully you can see it. If I can share the screen with you guys. Share. Just 1 second. Just going to share. Okay, so hopefully I'm going to rewind. Maybe now you can see it. So what we're going to see right now is a smooth signal fading into frequencies. Okay, this is exactly what I mean by a Fourier transform. You can see a smooth time signal, right? X as a function of t on the y-axis, t on the x-axis, okay? And you can see that smooth time signal after the Fourier transform, right, now becomes a frequency space function, okay? So again, I've rewinded it to show you the simulation, okay? So X as a function of t, right? We have a smooth time-based signal, right, for a Fourier transform, okay? And after applying the Fourier transform on that X of t function, this is what we get after, right? We get in our frequency space, okay? And you can see it's somewhat more bell-curved, if that makes sense. Okay, so I just want to show it to all the new people who don't know what Fourier transforms are. It's a frequency space. You see that there's a bell curve. So it goes from one function transformed to another function. So you can see it from sinusoidal to sort of a bell curve type of shape. Okay. All right. Any questions on that? Okay, so that's one thing when it comes to Fourier transforms. Okay. All right, so we'll just go back. We're going to go back to sharing the whiteboard. If there's any questions, please let me know. Okay. Let me know if you have any questions. All right, so let's go to the whiteboard here. Hopefully you guys can see it. Can you guys see the whiteboard? I'm back on the whiteboard. Okay, just let me know if you can see the whiteboard. I'm assuming you can. Okay. So we're at Fourier transforms again. Okay, so as I mentioned, Fourier transforms, right, just a superposition of complex signals and pretty much the decomposition of those sinusoidal waves give us a Fourier transform. Okay, now this is the way we calculate a Fourier transform. Okay, so let's say, for instance, very basic example, right? I'm just going to do a very basic example. If you have f of t, right, so let's go here. Okay, let's go to the next page. Okay, so let's say you had an example. Very basic example. F of t. So f of t is equal to e to the negative at. Okay, where let's say a strictly greater than 0. Calculate very basically. Calculate. Let's say this, like the Fourier transform of e to the negative at. Anyone know how to do this? I already know just another internet guy knows how to do this. Okay. Just 1 second. Let me stop share. Let me go back. I don't think it's shared. Let me share a screen. Sorry about that, guys. I'm gonna go back here. Share. Go to whiteboard. Anyone know how to calculate this Fourier transform? Okay, sorry about that. Just another guy. Yeah, it was just technical difficulties. Yeah, temporary technical difficulties for like 1 minute. Yeah, it looks like the whiteboard was acting weird. So this is a very basic one. We're just getting warmed up. How would we calculate this Fourier transform? No. Anyone know how to calculate this Fourier transform? In the meantime, just give me a moment. Someone just messes me. Merry Christmas. A friend of mine, I think, is up here. Let's see if they're. Just 1 second. He's just messaging something about later. Yeah, I think he's just. Oh, crazy people. I think they're. Yeah. Okay. All right. Yes. If anyone knows how to calculate this, anyone know how to calculate this Fourier transform? Remember, I mentioned that the Fourier transform, right, is just an integral, right? So how would we calculate this guy? Fourier of e to the negative at. Anyone have any ideas? Don't leave me hanging, right? So just look at the definition here for a Fourier transform. Okay, so I'm going to show you how to calculate this. It's very straightforward, just using the definition, right? So the way we're going to do that is, right, Fourier transform, if you all remember, is the following, right? Fourier of f of t is equal to integral from minus infinity to infinity, as you all know, is f of t times e to the negative I omega t dt, okay? Then from here, this will be the integral, right, from minus infinity to infinity. Now, I'm going to get to the bounds in a second. F of t is e to the negative at, okay? So e to the negative at times e to the negative I omega t, e to the negative I omega t, right? dt. That's the first thing. Input what the function is, correct? All right? That's the first thing. Now, we've got that. We have this integral here, okay? Now, what I'm going to do is, this is e to the negative at. E to the negative at. All right. What are the limits of integration on this function? It's not always negative infinity to infinity, by the way. That just means it can range along the entire domain. That's all it means. It doesn't mean that all the time that's what it is. Okay. So what does that mean? If my integral is can range from minus infinity to infinity, and f of t equals e to the negative at, what would be the domain? What are the limits of integration, I'm asking? If anybody knows. Yes, just an internet guy. How did you figure that out? Good. Just another internet guy knows exactly what he's doing all the time. Yes. How did you know that? Yeah, very good. I just want to make sure. How did you know? Making sure you understand conceptually why. Right, so 0 to infinity, right? And then the next step would just be doing this, right? Integral from 0 to infinity of e to the whole power. These are the same basis, so obviously I can say this negative at plus I omega t dt. Okay, factoring out the t. 0 to infinity. I'm going to use a different color here, by the way. I want to see if anyone responded. Yeah, exactly. Doesn't exist below 0. Wouldn't make any sense if it exists below 0, actually, along that domain. Okay, so now we have this integral here, right? So 0 to infinity, right? E to the negative, parentheses, right? And this is just going to be a plus I omega, parentheses, t dt. Right, so pretty much we have a complex number in the exponent, okay? All right. So that's what we're left here. So how would we integrate that? How can we integrate from 0 to infinity of e to the negative a plus I omega and then t? How do we do that? E to the whole power of negative a plus I omega. Remember, only, well, a plus I omega is a constant, by the way, so think of it as a number. How do we integrate that? Yeah, exactly. It's just a constant, right? So in reality, if we were to do our substitution here, right? If you let, right? In reality, what Justin, another internet guy, is saying is that he's saying in reality, you do substitution and take a plus I omega as a constant, let u equal to a plus I omega by t. Therefore, du will be a plus I omega, and then parentheses dt, because I'm taking the differential, right? Resubstitution, differential u with respect to t divided by a plus I omega. So then I get du divided by a plus I omega. And this is equal to your dt. You would substitute this in here. And you substitute all your u's and your du's appropriately. Okay? Okay, hope that makes sense. All right, so then you get integral from 0 to infinity of e to the negative a plus I omega. A plus I omega, we know here is our u, right? So this is like negative u, right? This whole thing here is negative u for this. dt is just going to be du divided by a plus I omega, okay? And then from here now, this integral from 0 to infinity, I can move that in the front. It's a constant, by the way. So I'll make sure anyone else is in here. Anyone else have questions? Just let me know. Anyone can ask questions. They can be math questions. They can be Christmas questions. Doesn't matter. Okay, so now we have this, right? So we have this integral here, okay? Then you're going to notice I get 1 all over a plus I omega, right? And then integral from 0 to infinity, e to the negative u du, okay? And if you know the integral of e to the u, it's very easy. It's e to the u. So this becomes negative 1 all over a plus I omega e to the negative u from, I'm going to say from 0 to t. I'm going to put a limit here, actually. It's better to put limits. Is this better to put limits when you're doing improper intervals? It's showing that you're approaching something here, right? So limit as t approaches infinity, right? Of, sort brackets, we'll do 1 all over a plus I omega e to the negative u from 0 to t. I'm going to see if there's any questions. Any questions? Okay. Let me know if you have any questions, guys. Okay. So right now we have this limit right here. Okay. Now all we need to do is, right? So we have it in terms of u. Okay. Right. And we took our limit from 0 to infinity, 0 to t. Okay. All right. So this is going to be the limit as t approaches infinity. Okay. On square brackets. Okay. 1 all over a plus I omega, right? So a plus I omega. I'm trying to make room here. So a plus I omega, and this would be e to negative u. We need to input what our u is. Okay, what was our u? By the way, I'm going to use a different variable. I should be using c or something because I already have t's that I have to resubstitute in. I'm going to say c approaches infinity, but it gets confusing. C is approaching infinity. Okay. So first off, we need to replace the u, for our u substitution, because we were integrating in terms of t, so a plus I omega t. So a plus I omega t, and then boundary conditions from 0 to c. Any questions? Any questions yet? All right, so I think assume that everyone is following. Okay. What you're going to notice here, right, is you're going to get the limit as c approaches infinity, right? All in square brackets, 1 all over, right? A plus I omega, right? We input the upper and lower limits of integration, so it becomes e to the whole power of a plus I omega times c minus 1 all over a plus I omega e to the, well, if I input t here for 0, this becomes e to the 0, right? Very straightforward, right? And then this limit will obviously go like this, right? Limit as c approaches infinity. Okay, 1 all over a plus I omega e to the a plus I omega by c. E to the 0 is 1, so it becomes negative 1 all over a plus I omega. And this would be a negative here. I think if we get a negative. Yeah, because negative u. Okay, any questions on this? Or any other questions that you would like me to answer? Anybody at all? Hopefully, Apodikolu is still here, right? So I make sure you guys are still in the chat. Okay. Let me know if you have any questions. Things are going to get more interesting. I just have to repeat this because it's important, especially for those of you who don't know what a Fourier transform is. You won't understand. I mean, you will and you won't. It's not like I'm going to go into doing the new stuff today on partial differential. Well, we're going to look at some type of partial differential equation that involves this, but we won't do to solve the problem. We'll just talk about it conceptually, the history about it. Okay. All right, so we have this limit here. Okay, now I have to allow c to approach infinity. Now, hint, hint. Can anyone tell me what's happening with this graph here? Right, if we were to figure out, it's really important to graph functions. That's why you can understand the behavior of what's happening to this as c approaches infinity. So if I have an exponential decay curve as c approaches infinity, well, if c approaches infinity here, what happens to e? Let's look at the graph. Think of it this way. Here's Santa's sleigh. Santa's on this curve here, or this ramp, you can say, and he's going all the way down, right? Right? Here's Santa. Ho, 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 ho. I can't draw. But he's going all the way down the ramp, okay? What happens as Santa approaches this asymptote, you can say? It's going to go to 0, right? 0, right? As we go down this ramp or this curve here, approaching the asymptote, this whole thing has to approach 0. So e to the negative anything is going to 0. So this whole thing here is 0. So that's 0. This is negative 1 all over a plus I omega. So negative 1 all over a plus I omega. And that's our Fourier transform, okay? Our Fourier transform, Fourier, right, of f as a function of t is equal to this. Now, I need to explain a bit more here about the Fourier transform, not just the mathematics of it. I need to explain what it means, okay? When we were talking about the definition of a Fourier transform, right, the superposition of complex signals, right, and its decomposition is just the decomposition of the complex signals are just individual sinusoidal waves, right? That's the physical definition. However, though, a Fourier transform is transforming from one domain to another. So we want to transform from the t domain to the omega domain. Okay. So the point here is you go from the t domain to omega. Just putting an extra note here that may be handy for you guys. Note. Putting on the first page. Note. It converts converts from T domain to omega domain. It converts from T domain to omega domain. So first it starts as a function of T, f of T, and then this will come out as a function of omega. Any questions? There's no questions. I assume that we're all good. Okay, let's continue. All right, so we have this guy next on the list. As I mentioned, this list, I may not follow it to a T tonight. It is Christmas Eve. I hope you understand. I don't want to bombard you. That's the only thing I was only going to bombard you guys was with that integral. So we've done 1, we've done 2 frequencies. Frequencies as structure. I'm going to talk about that a bit more. It's pretty much what I mentioned. Okay. As I mentioned, right? Whether they're Fourier transforms or frequencies in general, Fourier transforms a frequency. Okay. Frequencies pretty much they can be decomposed individually into sinusoidal waves. Okay. So the breaking up of the decomposition, as I mentioned, of a frequency either comes into some form of sinusoidal wave of some sort, and the structure of it is very important. Okay. That's why I want to mention is that the structure of it is very important. All right. And what do I mean by that structure? What do I mean by the structure of frequencies is important? What do I mean by that? Anyone take any guesses? Anyone take any guesses? Okay, I'm going to show you another simulation that will be handy for you to grasp. Okay, let's go to desktop again. I'm going to stop the share. Okay, and then I am going to, just give me a moment. I'm going to share screen with, undo the window. We're going to do, yeah, I'm going to do the window. Just give me a sec. So I'm going to go up to the second simulation here. Okay, and then I'm going to go back here, and I'm going to see if you guys can see what I'm doing. Okay, so as I mentioned, we're going to be looking at a time signal, right? Interesting time signal. Okay, so I'm going to show you exactly what I'm talking about here. I'm going to apply a Fourier transform on this guy. Okay, so time signal is on the left. Okay, so let me show you again. It goes pretty fast. The simulation I made with the programming went a little too fast. So the time signal is here, right? X is a function of t, time on the horizontal axis. After applying the Fourier transform as x is a function of t, right? As you guys can probably visualize algebraically. So this helps geometrically and algebraically, right? Because you can see that you would have to, if I want to apply the Fourier transform at x of t, it will just be integral x of t e to the negative omega t dt. After taking the Fourier transform, this is what we end up with, is a frequency domain. Okay, and our graph actually ends up being a bar graph of some sort. Okay, so it doesn't necessarily. Here's the way I want to put it. I should be more precise. It doesn't necessarily mean that's going to be a sinusoidal wave. Okay. Right, so let's do it again. Right. But what it means, though, is that the frequency wave itself can be decomposed into some other forms of waves or of some sort, some other graph of some sort, after the Fourier transform has been applied, right? So then from the time signal domain to a frequency spectrum domain. So time signal domain was a function of t. Frequency spectrum domain was a function of f or omega or some sort. If we set x as a function of f of t, we're going from t space to omega space. We started in t space, the time domain signal, then we ended up in omega space. Okay, does that make sense? Right, so we went from t space, the t domain, right, which was the time signal that we started off with. I just want to reiterate. Time signal is here. Okay, and then you can see on the other graph, we went to omega space because we went x as a function of f of t, which will give us a function of omega. So we went to the omega domain. Okay, any questions on that? Good. Justin, another guy is getting it. He's getting it algebraically and geometrically now, it seems. Excellent. I'm glad to hear that. Okay. All right. So we looked at frequencies as structure. Anything else if you talk about frequencies? Not really. We can look at something called a heat equation and why Fourier solved it. By the way, when I mean Fourier, I'm not going to talk about Fourier transform. Well, yes and no. Anyone know what a heat equation is? Please let me know. Oh, very good. Yes, I've done something similar with short time Fourier transforms computer science. Oh, good. Okay. Yeah, and there are and there's different types of Fourier transforms, by the way. I just want to let you know, and spectrograms with STFT sorts of Fourier. Yeah, that's right. That's right. So Justin here, guy, is right on the ball. Yeah, exactly. Fourier transforms. I didn't know in computer science they have them, but no, I'm not surprised. Fourier transforms. We used to be discussing the applications. The applications are very interesting, right? Yes, it involves integration, but this application has a lot of applications in areas you wouldn't think of, as I mentioned, and as Justin and the internet guy mentioned, it has applications in signals, frequencies. Let's see what else. Waves. Lead us to the wave equation. Hopefully, we can look at it a little bit. Obviously, I'm not going to solve the wave equation and the heat equation mathematically today because that's just a monster. But I'm going to show you the framework, sort of how we go about it a little bit, okay? But waves, and even when I mean frequencies, even for something like musical frequencies as well, okay? If you use Fourier transforms to evaluate musical frequencies, you can do all sorts of stuff. You can make scales, you can do all sorts of things. Right? So it's really interesting, actually, if you want to learn more about it. Okay. Okay. Have any of you, I know this is off topic, but it is Christmas, though. Have any of you watched the movie Matrix? Anyone ever watched the movie Matrix? I know this is off topic. Well, it's not off topic. It's still mathematically based. Anyone watched the movie Matrix? Okay, perfect. Oh, and you also heard about the heat equation. I never used Fourier solving or anything, so this will be new for me. Okay, yes, we're going to talk about that. But first thing is, we're going to be talking about, about the Matrix. So back to that. So in the Matrix, you've seen the Matrix at the end, there's this old man, right? He's the architect of the Matrix, according to the movie. Okay. Now the Matrix, what they're talking about in the movie, actually, they don't really refer to it, but they're also referring to it as some sort of a mathematical imposed world of some sorts, where everything is run by a simulation of the matrix. The matrix is supposed to be, if any of you have taken linear algebra, you know what a matrix is, right? Where you have your elements in your matrix, your rows, your columns, and stuff like that. So, that type of stuff, right? That the old man is talking about, right? Is really interesting. He talks about how everything is everything in reality, it has to do with the matrix and stuff like that. So, hey, it's really interesting how that comes up. And the reason why I bring that up is because that old guy looks like Santa Claus, if you've noticed. If you found that funny, he sort of looks like Santa Claus. Yeah, I think Justin and guy sort of gets it. Yes. Yeah. Looks just like this looks like Santa Claus. If you notice the old man at the end. Yeah. So I thought it was pretty interesting. We're talking about math, and we're talking about sort of the Christmassy type stuff today. So yeah, I thought it would be funny to bring that up. Looks like Santa Claus, and he's talking about matrices. Anyways, let's get back to it. talking about linear algebras for another time. I'm mainly talking about topics from my book, again, from Advanced Integration Techniques, which is, as the book says, advanced integrals. So if you enjoy solving and learning more about advanced integrals, specifically the theory about them and how they can be applied to your courses or your interests, your everyday mathematical curiosity, this is the book for you, right? So you can inquire with me about it if you want to buy it or anything else. Or, as I mentioned, tutoring as well. I'm always available for one-on-one lessons, and you can reach out to me on these concepts if you want to learn much more in depth. I can get into some really crazy stuff with you that you will enjoy learning. Okay. All right. So let's go to. Oh yes, Justin guy gets the Santa Claus thing. Yes. Yeah, that's. I thought I'd bring it up. I had no choice. It's Christmas time. I need to bring up a funny pun. Too bad he didn't have a sleigh in that, so that would no. But anyways, thought I had to bring it up. Okay, so let's discuss the heat equation. Okay, so page 2. All right, so the heat equation. Okay, so the heat equation. So the heat equation. Now, before I give you the equation itself, what's important is also to know what it is, what it measures, and it just measures the best distribution of heat, like the best, how to explain it? Yeah, the best area of distribution of heat. Okay, so the heat equation, I'll just say definition. It's the best. Did I say best? No, I shouldn't say best. The targeted location. A targeted, so I'll just say targeted location of distribution of heat. A targeted location of distribution of heat. The distribution of heat which is concentrated, in a particular spot, I'm going to get to the equation in a second. Oh, no, I hate when that happens. Thank you, Justin. When you get back and forth from the desktop, thanks again. Yeah, it just gets annoying. Thanks so much. I appreciate it. Okay. Yeah. So as I was mentioning, so here's the heat equation that I'm talking about. Okay. You're able to see it now, right? I just want to make sure you guys can see it. So let me know if you can see everything. Yeah, you can see it. All right, perfect. Okay, so back to it. So the heat equation is just a measurement or a targeted location of the distribution of heat, which is concentrated in a particular spot that we want to look at. Okay. Now, I'm not going to put, I'm not putting boundary conditions. It may not be as precise, but I'm going to give you the general laydown of how a heat equation is, how it looks like. Okay. All right. Just give me 1 second. Someone is, I think I have people giving me Christmas messages. Ah, great. Yeah. 1 second. Okay. All right. Yes. All right. So we're going to look at the specific equation, right? So it's di u Right? So di u di t is equal to k. K is a constant. Di squared u di x squared. Right? So di squared u di x squared. Okay. This is known as a partial differential equation. That's how we use partial differential equations to calculate the heat equation. Okay. All right. This is some really cool stuff. Okay. But here is this is the general formula of the heat equation. Okay. Is U the heat? Okay. Very good questions. Very good questions. Now, U is a function of both the position and time. Okay. So it's a function. Now, in terms of the heat energy, in terms of the physics of it, I wouldn't actually know if U is the heat energy, not specifically. And usually the equation doesn't say anything when I've done heat equations in my mathematics classes, mathematical methods classes, or partial differential equations. No, they have to do anything with heat energy. No. No. But what you do need to know, which is important, is that U is a function of both position and time. That's what U is. And you need to know that's a function of both. Otherwise, you can't mathematically calculate. I'll get into that in a second. All right. So, so this is what we've got here. But before I show you how to deal with a partial differential, how to deal with this specific partial differential equation, I'm going to get really fast into it. Separation of variables. Okay, separation of variables. When you talk about this, if you've taken any introductory calculus classes, or well, you better have, otherwise you're not going to understand my lectures at all. Yeah, you need to have a very strong, foundation in introductory calculus for sure. But if you've taken any mathematical methods classes, any differential equations classes, they will talk about something called separation of variables, and they can be handy for solving any type of differential equation, especially when whether they're regular differential equations or partial differential equations where you have to deal with functions of multivariables and stuff like that. Okay, so we're going to look at separation of variables. Okay. Separation. I can't spell tonight. That's okay. Separation. Just 1 second. Someone's giving me a thing here. Separation of variables. Okay, so hopefully some of you are familiar. Yeah, you get it. Yeah, you get it. Just an internet guy gets it. Hopefully the rest of you get it too. I want you guys to tell me if you're understanding. I need to connect with you guys and see if you understand the concepts, right? That's my job. I want to make sure you understand what is going on here, that it's not some alien language, okay? All right, so we're going to learn separation of variables to help us to analyze pretty much any partial differential equation by mathematical methods, okay? So definition. Okay, so DEFN. Let U be some, I'll say here, that's what I'm going to say. Yeah, let U as a function of x and t be a generic function. A generic function. A generic multivariable function, I should say, to be more precise. Multivariable. I should be saying multivariable function. Multivariable function. Multivariable, be a generic multivariable function such that U as a function of x and t can be modeled as I'll say over here, x, capital X, as a function of x, and capital times capital T as a function of t, right? So if you use a function of x and t, then it's equal to capital X as a function of x times capital T as a function of t. Then what we want to do is with this function, right? Separation of variables, right? So by, I'll say by separation, just 1 second, what time is it? Separation of variables. We want to isolate right, functions of x on one side, functions of x on one side, x, I'll say x, highlight here x on one side, and functions of t on the other side, functions of t on the other side. Right? That's mainly what we're doing with separation of variables. Okay, does that make sense? All right, so this is what separation of variables allows us to do. Okay, so just to give you a hint of this, what you would do is when you have separation of variables, so since du dt, let's say for the example, the heat equation, right? Okay, I have to give you a bit more, but you can play around with this in your own time, right? Right, so maybe you can conclude something, but you still need to know some superposition properties, okay? Yeah, separation of variables, right? So it's just like saying, for instance, if you've done basic differential equations, right? You know that, let's say if you had x squared y is equal to x, then you would want to isolate y is on one side, x is on the other side, right? I should be saying like something like this, right? X squared over x, 1 over y on one side, right? And then, well, this would be derivatives. This would be differentials, actually. Sorry about that. Let's say you add 2x dx equals dy, right? Dy over y, let's say. And then what you would do is you just get x, 2x dx. This has already been isolated for y on one side, x on one side as function of x and function of y. Then what you would do is you would integrate both sides, right? Integrate both sides of the equation and then add an arbitrary constant. Same thing with this. Same thing for separation of variables for multivariable functions. Okay. I'm not going to go into it because this is supposed to be a light class today. All right. But you can play around with it. Play around with the heat equation during your own time. Okay. So play around with this guy during your own time, if that makes sense. All right. All right. So we're going to look at another simulation. I feel like modeling helps. Modeling helps understand concepts and makes things more interesting instead of me doing chalkboard after chalkboard after chalkboard all the time of crazy equations. Okay, so let's get back to it. I'm going to go to the desktop. Just give me a second. 1, 2, 3. I think it was this guy. Just give me a moment. No, that wasn't it. Where are we? Number 4. I think it's the 4th one. Just give me a moment, guys. Okay, let's go back. I'm going to share screen. Okay, I'm going to share my screen. Okay, we're going to go to window, go to the simulation. Okay, what we're going to look at here is a very interesting simulation, and I think you guys will find it neat. So as you can see, the programming simulation shows us a heat bump, okay? And a heat bump can give us a Fourier mode transformation at different rates, okay? What you're seeing here is as on the left graph compared to the right graph, right? So there's a comparison of two graphs, okay? So comparison of two graphs here. One graph, okay, on the left-hand side, u, the generic function as a function of x and t, is a heat bump of x and t, right? You see that it oscillates upwards, then it comes down, declines downwards again, okay? Then you can see that as time is increasing, we get a higher value of n, and we have a decay actually, some sort of exponential decay of e to the negative k, k squared nt, where k is a convexity constant. I forgot to mention k is a convexity constant of the heat equation. Okay, so as time is increasing, what you'll notice is that heat bump now is like, sort of plateauing or coming down in a sort of gap there, right? As you can see, right? So you can see that the curve there is really plateauing, right? So it goes from upwards and down, right? So right there, and then it sort of starts to decay, sort of, right? Use function of xt. In that case, in our case here, u is the heat bump, right? And that heat bump equation, after the transformation, becomes Fourier modes with amplitudes, different amplitudes of the bar graph there. Okay, so let's look at it again. All right, so you can see this is actually after by solving the partial differential equation, what happens graphically. Okay, so you can see here, right? After solving the heat equation, the partial differential equation, right, we get some very interesting graphs here, very interesting geometries. Okay, so the heat bump x as a function of t, right? All of a sudden, when it's transformed, solving that heat equation requires a Fourier series, actually, Fourier series transformation. I didn't talk about Fourier series, but it actually gives us Fourier modes here, right? Which is the right-handed graph afterwards. So the comparison before the heat pump function graph compared to the Fourier modes function graph afterwards. And you can see the right-hand side here, we have Fourier modes, right? The Fourier modes is no longer some curve. It's now bar graphs. So you have a bar graph at n equals 1. The bar graph is bigger. At n equals 2, smaller. N equals 3, much smaller. Okay. Any questions on that? Hope you found that interesting. Okay, we're going to go to the whiteboard again. Just give me a sec here. Here's the screen again. Go to the whiteboard. Oh, I'm really glad you like it, that's another guy. I'm really glad you like it. Great. Perfect. Thank you so much. I really appreciate it. I'm trying my best doing these. Okay, we're going to go back to, I'm going to go back here. Okay. So we're talking about the heat equation, and I was talking about separation of variables. As I said, again, today, we're not going to have time to do these, right? I'm trying to take things light. Yes, this is me being light. Okay. This is me not being rigorous. Okay. For those of you who watched my other videos, you know how much work and rigor I put into my live shows and also my streams as well, if you've been watching. But here is just I'm putting up definitions and simulations. My simulations are in all my other videos too, but today is just mainly definitions. Okay, and just putting up the definition, no proofs, no examples, no computations. Okay, so that's a little bit backbone to the heat equation. It's solved using something called a Fourier series. So what you can do is you can look into what a Fourier series is, or you can consult me on if you want to learn about Fourier series and how to solve these. I can help you, right? I can help you solve these with like really, really interesting stuff. You'll learn a lot here, okay? They're really handy for physics and engineering classes. Okay, like using Fourier series to solve partial differential equations, whether heat equations, wave equations, doesn't matter. You can consult me. I'm always available. Oh, thank you very much. I try my best with the programming. That's what it is. It's code and everything, and I create the simulations. Yep, try my best on them. Thanks so much. All right, let's get back to it. Okay, so the heat equation that we had, right? as I mentioned, either you can look into it, or if you need more help, you can always consult me for expertise, right? When it comes to this, I'm always available for solving these types of problems, right? I'm always available. You can either reach me at my link, www.stem1online.com, right, for help on these. Or if you want to learn more, right? If you want to learn more on how to solve them intrinsically at a deep level, okay? So we've talked about the heat equation, why Fourier. I didn't talk about why Fourier. I'm going to maybe just give a little light definition here, or formula on Fourier transforms. Should I? Oh, no, I don't have time tonight. But I did give you sort of a why with the simulation, because that simulation was talking about going from the x of t time signal to a Fourier space. I'm using a Fourier series, Fourier series axiom, not a Fourier transform, a Fourier series to be more precise. So I did answer why I'm using Fourier. Okay, I talked about the simulation of the heat diffusion. Wave equation and oscillations. One last thing we're going to discuss. Okay, so wave equations. Any questions? Any questions at all? Yes, just an errand guy. If you want, you can always consult me for lessons if you're interested in learning this stuff. Okay, I have a team. It's me and some other people. We do coaching and advanced tutoring in these areas. Cool, cool. I like that. I like that you like it a lot. Perfect. All right. So let's go to it. I was talking about wave. I think it was the wave equation I want to talk about next. Yeah, one last thing we're going to talk about tonight. I think we're going to go to the wave equation. Okay, so wave equation. Okay. Wave equation. Wave equation. Yeah, that's what we're going to talk about. You talk separate variables. Wave equation. Okay, so wave equation. So there's something called we talked about the heat equation. That's one partial differential equation. The other one is the wave equation. I want to use blue and yellow. I feel like white gets boring sometimes for a title. The wave equation. The wave equation. Okay. The wave equation. Right, so the wave equation, I'm not going to get into it that much, right? But I am going to talk about, I'm going to talk about pretty much it's for solving anything to do with waves. Not anything to do with waves, but any type of wave, like a wave phenomenon. Okay, so definition. I want to see if anyone came in, has questions. Okay, so no one yet. No one else. All right, so right now, definition of the wave equation. Okay, so wave equation. All right, let's see here. So what it is, the wave equation. Wave equation. It's going to model. This is models. Models waves. Models waves of a string. Okay, wave equation. Should I say models? Yeah, models. Models. The wave of a string. Also, wave of a string in terms of position and time and stuff like that, right? Wave of a string. So, for instance, if you have something maybe something like this. Maybe you have waves, okay, like this of some sort. U as a function of xt and whatever else. All right. All it's doing is just it's a mathematical model of a wave of a string, right? So what I mean by string is I mean like a physical string, right? You whip it, and once you whip the string, right, it starts forming waves. So we're going from a physical model to a mathematical model, okay? So as I said, you can whip a string, right? And then after it forms waves and stuff like that mathematically. Okay. Again, u as a function of xt is very important. And the way we measure this is using di squared u di x squared equals c squared. C is the speed of light times di squared u di t squared. This is the wave equation. Okay. Oh, wow. Just another guy. You're pretty advanced in mathematics, I see. I'm pretty impressed. What year are you again? I forget. Because I know you're in university. I'm just not remembering exactly for oscillations, but that's about it. Yeah, you did with oscillations. And you're in computer sciences. The first year. Oh, that's impressive. The fact that you've seen certain types of ODEs, so as I meant, and all the other stuff as well. What uni do you go to again? Oh, okay, so you probably like learning stuff on the side as well. Okay, nice. Perfect. Again, you're in the right place. This is exactly who we help: hobbyists and undergraduates, students, both in reality. All right, so we're looking at the wave equation, right? So we have this guy right here, right? Now, as I mentioned, that this models the wave of a string. Okay, u is a function of x comma t. I'm going to see if I had made a model actually. Oh, you're at Cornell. Oh, that's a very good university. Yeah, that's an Ivy League. Oh, good for you. Excellent. All right. Yeah, they got good programs there. Yeah, very good programs. Yeah, right. So let's go to, if possible. I'm going to see if I made. I don't think I made a what's it called? A simulation. Made a simulation for what's it called, for the wave function. Not wave function. The wave equation, like showing you how it works visually. Let me just still check. I'll be right back. Okay, let me see if I did anything. Oh, I did. Give me a moment here. Okay, just give me just one moment. Okay, so I'm gonna go back. I am gonna go back here. Just 1 second. Okay, so I'm gonna go back here. And what I'm gonna do is stop share for a second. And then I'm gonna share screen. Go to the media player. Okay, so we're gonna look at a classic example of the wave of a string. Okay, so we got a standing wave. Okay, for those of you who've taken any physics classes, you probably understand what I mean by a standing wave. If you don't, that's okay. As long as you understand what a sinusoidal wave, as long as you know mathematically what I'm talking about, that's fine. Maybe physics-wise, you won't understand what I mean. Anyways, so a standing wave will imply a frequency type of oscillating function here. Okay, so again, right? We have u as a function of x and t, a generic a multivariable function of two variables. We start off with a standing wave. Okay, x position along the string. So x is the position along the string, right, on the horizontal axis. And you can see here the second graph gives us a frequency type of components here, right? Right. So we're going from, again, transposition from a standing type wave, a sinusoidal wave, to a frequency type of function. And that frequency type function is actually just bar graphs, right? And the frequency is going from minus the frequency f0 to positive f0, where f0 is to be an observed type of frequency that we're noticing here. Okay, so try to visualize that. I know that can be tricky, right? Try to visualize that. Okay, so here I'm giving you a mathematical visualization, but since at the same time this is an application to physics, you can also do like a physical type of visualization, if you know what I mean. Okay, it's not always easy to picture these, but the point is to help you get a better understanding pictorially of what I'm talking about. And it also helps your mathematical intuition when solving problems, actually. It's very important. Okay, so as you can see, both frequencies will oscillate, right? So both of these guys are having an oscillation type of effect, right? Both graphs are oscillating, right? So again, you can see the standing wave oscillating back and forth like that. Frequency as well is oscillating, the frequency function, right? I should be saying, well, the right one is a nodal frequency function. Anyways, that one with the bar graphs is oscillating as well, okay? So again, I just want to show this again because this is my favorite simulation that I made. I really like it. And you can see both frequencies are oscillating in phase. That's what it means to be in sync. They're both oscillating in the same phase, right? Standing wave, as it mentions at the bottom, I want you to pay attention, right? Right? So just give me a sec here if I can get this going. Both frequencies are oscillating in sync, right? That means they're oscillating in phase. They're not out of phase. They're in phase, right? Okay. And they both imply symmetric frequency components. Okay. All right. So let's get back to it. All right. So hope that was interesting. Okay. So let's go to share screen again. Go to share screen. Well, before I go to share screen, I don't think I need to. I think we've covered everything tonight. Again, this was very cool. I hope you guys enjoyed the content. As I said, tonight is somewhat of a light type of introduction to this topic of Fourier transforms and partial differential equations. Okay. Again, this is all concepts from my book, Advanced Integration Techniques. If you're interested in learning more about complicated integrals, integral problems, challenging yourself to maybe even open problems, my book is for both types of students who want to build up their mathematical toolkit in calculus, all areas of calculus, numerical analysis, complex analysis. This is the book for you. And or who want to really challenge themselves. There's a challenge section that is really, really difficult. So if you like to challenge yourselves with full mathematical rigor, then this is the book to get. It took me a long time to make this. It was 4.5 years, 5 years. Yeah, almost like 440 pages in total. Yeah, it was crazy. But yeah, you can always get a copy. The copy is in the link below if you're interested. Okay, either now or after you can get it, or if you just want to consult me when it comes to consulting and you want to actually learn more of these mathematical methods, you can again contact me. Just 1 second. Someone's contacted me. Christmas stuff. Let me see here, because I'm friends contact for Christmas. That's funny. No, that's not it. Nope. We have that. Oh, good grief. This is a crazy friend of mine is giving me a thing here. But yeah, as I mentioned, right, Fourier transforms and partial differential equations, right? They're not just about speed, right? Not just about speed and not just about, doing calculations. It's about understanding deeply concepts at a very deep level, algebraically, geometrically, and physically, right? That's the whole point to this lecture. That's what I'm going to bring home, right? Which is very important. Okay. All right, just 1 second. So, my friends are contacting me. Right. That's 1 second, guys. But as I mentioned, if you want personal guidance to understanding how this stuff works, you can always contact me, right? Always contact me through STEM1online.com for more information. My friend keeps. Sometimes friends can be a bit annoying. But yeah, if you want to learn at your own pace and you need a really good guide, you can get my book, Advanced Integration Techniques. And or if you want coaching, you want homework help, if you want personal tutoring, if you want any of that on these concepts, on these advanced integral concepts, or in other areas of math, physics, or anything of that nature, you can contact me for coaching, personal coaching as well. All right. Thanks, guys. Again, Merry Christmas. It was a pleasure. It's a pleasure always giving lectures to you guys. This is what I love to do. This is exactly what I was meant to do. So I love doing it. But that is it. Merry Christmas. And again, you should watch out for me. Oh, yes, you're welcome, just a learning guy. Yes, no problem. Yes, I really appreciate it. Thank you so much. And just want to let you guys know that I'm always available. My stream times and my live times. Live times I'm always on is Wednesdays, 8:30 p.m. Eastern. Okay, and the other days are just streams. So Monday is live, which is Wednesdays at 8:30 p.m. The other 2 days, what is it again? Thursdays. Thursdays is a stream, okay, at 7 p.m. Eastern, and Sundays at what is it like? Sundays can oscillate, streaming at 7 p.m. or sometimes in the morning, but you will catch me when you catch me. Okay. Again, Merry Christmas and Happy New Year. I will not be, on tomorrow, even though it's Thursday. I won't be doing a stream. It's supposed to be a stream tomorrow, but the reason why is obvious, Christmas time. But Merry Christmas and Happy New Year. Ho, 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 ho. Bye for now.